So our session is more a methods development session, and then we had the first talk today on the Free Energy Consortia by Hannah Baumann. She was a grad student with David Mobley, and then after that she moved to Berlin to work on the Open FE Consortia at Bayer. So looking forward to your talk, and thank you.
Yeah, thank you so much for the kind introduction, and thank you for having me here today to share with you a little bit about our work at the Open Free Energy Consortium. As we all know, and this I'm really excited to hear in a lot of talks this week, free energy methods are really broadly applied in industry, and that's really exciting to see. And on the other hand, also new methods are continuously developed in academia to really push the field forward. However, sometimes we can then have this gap that the new methods that are developed in academia, it's sometimes hard for academic groups to really maintain the software when like postdocs or grad students leave. And on the other side, industry really needs methods that work out of the box to be used on large scale in their active projects. And so we have this energy barrier or this gap there. And this is really the reason why the Open Free Energy Consortium was founded, that we're here to try and bridge this gap and to lower the activation barrier, to bridge the gap both of the delivery of the applications, but then also of the maintenance of the software. And so the goal here is, of course, to reduce cost and also duplication of efforts, that not everyone has to always cross this barrier, and to really ensure that the tools that we develop are sustainable long-term. And our goals and our mission here is to provide stability, to provide testing, and as we do the testing, also to help with best practices. Okay, and so now how do we want to do this? Our vision here really is to create this community effort together with academia and industry, and to bring this together. In order to kind of lay the groundwork there, we developed this package that's called Goofy, the Grand Unified Free Energy. And this is kind of the base layer. You can think of it as a foundation. It's base components that are reusable, kind of like a reusable free energy language that then others can put their methods in and contribute. Working together with academia here, our vision is really to create an ecosystem of interchangeable and swappable components. You can think of it kind of either as an app store or as like this children's game where you have all these different puzzle pieces of animals, and you can just like mix and match them to create these beautiful, maybe not real, but alchemical creatures. And the goal here is that a group could, for example, also just contribute like a part of it, so not like the whole pipeline, and still, because of this base layer and because of the tooling we provide, it fits seamlessly together with the other methods to really be used in this pipeline and be swappable. And the goal is here also to increase the visibility of methods, that hopefully a lot of people can use them. And a really important fact here is we have a technical advisory committee that's all over the world, professors that advise us and really guide us in this through the alchemical adventures, and also then help to create new collaborations with grad students in order to really build this community. And on the other hand, it's of course also really important to work together with industry, because in the end, that's where the method will mostly be used, and we want to make sure that everything we do really fits the needs in industry. And so just to take you a little bit into the process of how this looks like, basically we look at new methods, we talk to our technical advisory committee to get ideas of things that we could do, then we propose the things to our board, which is our partners that fund us, and then our board members, they can vote based on also the priorities in their company, what the next things are that we should work on. We have these monthly meetings with our board where we give scientific updates, where we receive feedback, direction, and also they help us with the prioritization of our tasks. And a very crucial thing is give us back experience from using our tools and how we can improve there. And we also really have just scientific discussions, and this is actually where the cycle also kind of closes, where we invite people from our TAC, from our technical advisory committee, to come to these board meetings and just give us an update on the new method they are working on, so to really grow this community. The software that we develop, everything is under the MIT license, which means that it's free to use. And it also means that it allows you to really expand it into a direction that you're interested in, and to make it, to just modify it for your in-house needs. And one thing I think is really exciting, people who are already doing that is ASAP Discovery. Josh Horton will be presenting this poster, but I just wanted to highlight this. They developed this beautiful pipeline to run free energy calculations at ASAP at large scale, using also open free energy. And so this is really cool to see how they were able to expand upon it into their needs. One of the components here is also Alchemy scale that can be used to run large-scale OpenFE calculations. And David Dawson will also talk about this in a poster, so feel free to check that out as well. So far, I just gave you like a very general idea of our vision, where we're heading with this project. And now I just want to go a little bit in the details of what we've done so far. So Open Free Energy was founded back in 2022 with 13 industry partners back then. And in the first year, really, the project focused on this base layer that I told you about, like this foundation, this common language, as well as an RBFE workflow based on the Perseus package from the Codera lab that's OpenMM based. And also adding full support for open force field that we, of course, collaborate very closely with. In the second year, we then added supporting tooling, and I will be talking about some of these in this talk: Cartograph and 3D-based atom mapper. And then we took over maintenance of the LOMAP package from the Mobley lab for ligand network planning, as well as the Cineba package from the Codera lab for like simulation analysis. And we just very recently, I think last week, released our first stable release, the 1.0. Thank you. Yes, I'm very much looking forward to you trying it out and letting us know how it works in your hands, what things maybe you run into, ideas you have on how we can improve. This is mostly RBFE. We allow charge changing transformation. We have an absolute hydration-free energy protocol, hopefully very soon, absolute binding, and then just also plain MD simulation for you to equilibrate your systems. This year, some of the things we're really excited about is a large-scale industry benchmarking together with our industry partners to really see how the method performs out in the wild, and as well as adding new methods. There we are looking right now into scaffold hopping using the separated topologies approach, as well as adding, so far everything is OpenMM based. We want to add another MD engine, GROMX, using the PMX package from the De Groot lab, and Peter Scapsis, who has also worked a lot on that, as well as custom OpenFF parameter fitting. And then if you want to try this out, there are different ways on how you can use OpenFE. One is through our command line interface, where we have this pipeline. You come in with your prepared systems, and then you can plan, run, and analyze the calculations using these 3 commands, and then get your MLE-derived delta G values out. So very much in the beginning of the talk, I told you about this idea of a decentralized ecosystem of these swappable components of our chemical creatures. And I just want to show you on some examples of how this already looks like right now in our package, where we already have some of those swappable components. On the one hand, we have 2 different atom mappers, and I will be talking about that in a bit, LOMAP and Cartograph. We have different protocols, protocol based on equilibrium and non-equilibrium free energy calculations. And then different, of course, you can use different force fields, different OpenFF versions, also different partial charge generation methods. And I will be talking about that in a little bit. And so for the remainder of the talk, I really want to take you into some of the examples of how now this community effort looks like in practice and how we work in the consortium. And on the first, I want to just highlight how we develop new features like this cartograph atom mapper. Then we have other people who develop things within our ecosystem, and so this is really exciting to see the first protocol that was developed based on this base layer, this goofy package that we developed. And then, of course, a big part of our work, as we want to really have things around for long term, we have to maintain and validate things, and I want to show you a little bit about that. In our BFE calculations, we typically map ligands on top of each other and then only transform the atoms that are different between the two ligands in, like, for example, hybrid topology approaches. And this atom mapping is actually a quite challenging problem. A lot of the code is based on the maximum common substructure of the ligand. So this is like the 2D, the topology of the molecular graphs. And some things are quite challenging in 2D, for example, stereochemistry. So here we have two ligands that are just stereoisomers of one another. And this one atom mapper now here would have mapped this fluorine on top of this fluorine, which while in 3D you can see they are actually not close to each other because they are, the stereoisomer. And so here we would have sampled the wrong chemistry basically. And so we need mappings that really do this well. On the other hand, these MCS-based algorithms can become kind of slow, especially like the low map mapper we work with that is MCS-based. Once it gets into hundreds, thousands, or 10,000 of ligands, that can take a little bit. And so it would be nice to have faster algorithms. And so Benjamin Ries in our team worked on this atom mapper that is called cartograph. And this is now a 3D-based atom mapper that looks at interatomic distances and designs the mappings based on that. And he will actually be talking about this later, so I won't go into the details. You'll have to be patient and wait for his talk. But yeah, it is quite fast, which is really nice. And so what we can now do with OpenFE, with these swappable components, we have now these two swappable components, our two different atom mappers. We can just leave all the rest constant and just really benchmark the two atom mappers against one another. And so we did this here on the protein ligand benchmark set on these 9 systems. And you can see here, looking at the RMSE of both the delta Gs as well as the delta Gs, and then here also the Canel tau as a correlation measurement of the delta G value, that on these systems, both atom mappers gave statistically the same results. And so this was very promising to us that we do similarly than this well-established low map atom mapper while being much faster. Now, it's not just us developing new methods, also other people contribute. And so this is, of course, very exciting. So our protocol in OpenFE 1.0 is based on equilibrium free energy calculations, which go back to the Swansig equation, free energy perturbation, and the Bennett acceptance ratio, where we have a discrete set of lambda windows that we simulate until we reach equilibrium, and then sample at equilibrium, and then get the free energy difference using the Bennett acceptance ratio. We also we stop simulations and swap between lambda windows the configurations to enhance the sampling, so we do replica exchange. On the other hand, there's like non-equilibrium free energy calculations based on the Jasinski equality and the Crookes fluctuation theorem, where you run long MD simulations of the end states, you extract a snapshot, and then traverse the alchemical space through these fast switching transitions. And then analyze the free energy difference based on the probability of the work distributions and the Crookes fluctuation theorem. And Ivan Pulido from the Codera lab worked on this protocol. It's called non-equilibrium cycling. And now the new version uses the base components from OpenFE. And so we are in the current process of benchmarking now the two protocols against each other. Here's just like one example. This is the P38 system, again, from the protein ligand benchmark set. Here we leave everything the same, so we use the same mappings, the same partial charges, the same force field, everything the same, and just swapping out the sampling, and the results look comparable. And yes, we are working on benchmarking this more and comparing it more. Yes, and as we develop new methods and take new methods in, of course, we have to continuously validate. One thing we do is that, of course, every new release, every new major release, we benchmark against the older releases to make sure we still get similar results. So this is our new 1.0 release against the 0.14 on 3 of the protein ligand benchmark systems, and you see that we still get the same results within uncertainty. OpenFE is also used to validate different force fields, and so Lily from the Open Force Fields Consortium is going to talk a little bit about this in her talk. And we also do benchmarking, for example, for major OpenMM releases to also make sure that we still get the same results. And as we then will add new engines like ROMX, we would then also do the same to just really make sure that nothing breaks on the way. And as we do this, sometimes we do find these kind of problems. So these are results from a benchmarking of a new OpenFE version that was, I think, back in the summer, where suddenly we got these gigantic error bars. The error here is the standard deviation of 3 independent repeats. And this was quite puzzling to us, like why we suddenly got these large errors. And in collaboration with the Mobley Lab and Megan, a grad student in the Mobley Lab, we traced this back to the partial charge generation. As I think partial charge generation can be conformer dependent. And so one problem that we discovered here was that we generated partial charges for independent repeats and in the thermodynamic cycle again and again. And these tiny differences, as you can see here, is like really small difference in partial charges. They were able to lead to these large differences in free energy. And so if we use the same conformer, we were able to get reproducible results. But even we found when you and actually, Megan will be talking about this in her post, and I really encourage you to check it out because she was able to push this further and really investigate this more. And it's not just the conformer dependence, but also actually like the actual SQM minimization and antechamber. We saw that it can converge to different minima, which then leads to different partial charges and different free energies. And so this has been quite puzzling and interesting to us. And so we can now, again, as these swappable components, just compare different partial charge generation methods against each other. Here we're comparing against OpenEye ELF10 as our base gold standard, and you can see there are some differences. We also here are comparing a neural network-based partial charge generation method, NAGL from Open Force Field, that Lily will be talking also about in her talk, and this should then remove this conformer dependence. And of course, we do the scientific validation on the one hand, but a big part is also just in general software validation of our own stuff when things break, but also upstream packages like RDKit, Ember tools, where we have to, like sometimes go and fix things, and this is also just part of our work. And yeah, I hope you're interested in trying this out. We have like a showcase that walks you through these tools that I just introduced to you, and shows you how you can run these both in our Python API, but also in our command line interface. And please let us know if you have any questions there. And with this, I would like to thank everyone on the team. It has been a lot of fun to work together. I thank the Open Molecular Software Foundation for hosting us, and ASAP for collaboration. We thank the Percy's team really for all their hard work, all the software they have developed that we now also benefit from. Open Force Fields, the Mobley Lab and that collaboration, the executive committee, and I thank Bayer AG for hosting me. We thank our technical advisory committee that's been super helpful, and our industry partners. And I would like to take any questions that you may have.
Thank you, Anna. Thank you for a great talk, for presenting the OpenFE consortium, and to sticking to the time. We actually have time for one quick question before the coffee. So I think that everyone wants to move on to the coffee.
To the coffee, yes.
Okay.
Really quick question about how do you do licensing of all these different topics, of all these different projects, really?
Yes, so we all the software that we use also has to be open source. So everything we do has to be MIT, and so that's why also the packages that we can use are coming from that. Of course, for example, as you saw, we are benchmarking also OpenAI. If then our partners or if academics have an OpenAI license, then you can also, for example, use OpenAI to generate your partner charges. So these kind of things are then also possible. Yeah.
Okay. It's time. Before that, just one quick announcement. Thank you very much, Hannah, again. So, poster presenters, the poster boards are ready. We are still arranging the numbers so you know where you have to do it. Hopefully at lunchtime it will be everything ready. You can bring your poster up and then not hang it yet probably. That was one. And the posters can remain the whole 2 days, actually the whole conference. So please, if you are presenter on the poster session tomorrow, you can hang it today. That doesn't mean that you will not be presenting it today, but your poster will be nicely hung there and people can start looking at it and all that. And in the session that is coming after the coffee, there will be one slight program change. There will be one session that will be swapped, and but that will be introduced by the next chair. So, thank you very much and enjoy your coffee.